Queen's Bath. In the flourishing courts of the Renaissance, King Aldrich of Elmsford brought home a new queen, Lysandra, from a distant and mysterious kingdom in the east. The queen had one peculiar demand.
I demand, my baths must always be at a perfectly warm temperature, not too hot, not too cool.
The king, smitten by her charm and eager to win her favor, grew anxious. He pondered aloud during a council meeting.
How can I ensure her baths are always perfect?
None of the servants could promise consistency, for each attempt relied on guesswork. Desperate, King Aldrich summoned a renowned natural philosopher and inventor, Master Cornelius, famed for his groundbreaking work in sciences.
Cornelius, devise a method to ensure the Queen's bathwater is always at her preferred warmth.
For weeks, Cornelius toiled in his workshop, studying the nature of heat and experimenting with various devices. Finally, he invented a device he called the thermoscope, a glass tube filled with a special liquid that rose and fell depending on the warmth of the water. By immersing the thermoscope in the bath, Cornelius could measure the temperature with remarkable precision. He meticulously recorded the liquid level that corresponded to the Queen's ideal bath temperature. With this knowledge, the servants could precisely heat the water until the thermoscope indicated the desired level. When the Queen first stepped into a perfectly warm bath, a radiant smile lit up the palace. Thus, the Cornelius's invention forever changed the understanding of temperature measurement. The thermoscope became a foundation for future innovations.
In the late 16th and early 17th centuries, devices called thermoscopes were developed. These were the precursors to thermometers. Galileo Galilei is credited with inventing an early thermoscope in the late 16th century. The thermoscope consisted of a glass tube with a bulb at one end, partially filled with air, and connected to a column of liquid, often water, wine, or alcohol. Changes in temperature caused the liquid level to rise or fall due to the expansion or contraction of the air in the bulb. These devices lacked a numerical scale, so they couldn't measure temperature precisely. They only indicated relative temperature changes. Nevertheless, they paved the way for future advancements. Florentine thermometer. In the mid-17th century, members of the Accademia del Cimento in Florence, Italy, including Galileo's pupil Torricelli and others, developed sealed thermometers filled with alcohol or mercury. These were more reliable because they were not affected by atmospheric pressure. They made fundamental contributions, being the first to develop graduated alcohol thermometers. The Florentine thermometer introduced a more standardized approach, but still lacked a universally accepted scale. While the tools lack the precision we take for granted today, they represent the ingenious attempts of early scientists to quantify one of nature's fundamental properties, the temperature. Empirical fixed points. Before standardized scales, some scientists and engineers used specific physical phenomena as reference points, such as the freezing and boiling points of water, the melting point of wax, the temperature at which butter melted, the human body temperature, often referred to as blood heat. Development of scales. The idea of assigning numerical values to temperature didn't emerge until later. The first standardized scales, such as those by Ole Romer, 1701, Daniel Gabriel Fahrenheit, 1724, and Anders Celsius, 1742, built on the principles of these earlier methods. The Romer scale is based on the freezing point of pure water being 7.5 degrees and the boiling point of water as 60 degrees. Romer's work had an important influence on Fahrenheit, a manufacturer of barometers and thermometers. Fahrenheit began experimenting with mercury thermometers in 1713 and was using a modified version of Romer's scale for his thermometers, which would later evolve into his own Fahrenheit scale.
The name is pronounced as Ole Rømer.
Fahrenheit scale. Developed by Daniel Gabriel Fahrenheit, 1686 to 1736. Year, 1724. Key concept, based on a mixture of ice, water, and salt, as well as body temperature. He chose 3 reference points. 1. 0 degrees Fahrenheit, the temperature of a mixture of water, ice, and ammonium chloride, a salt. 2. 32 degrees Fahrenheit, the freezing point of pure water. 3. 96 degrees Fahrenheit, later adjusted to 98.6 degrees Fahrenheit, the temperature of the human body. The Fahrenheit scale was later redefined to make the freezing to boiling interval exactly 180 degrees. Celsius scale, developed by Anders Celsius, 1701 to 1744. Year, 1742. Key concept, based on the freezing and boiling points of water. Anders Celsius, a Swedish astronomer, proposed a temperature scale in 1742 using the freezing and boiling points of water as fixed reference points. Celsius divided the temperature range between these 2 points into 100 equal parts, creating a linear and uniform scale. Each division represents 1 degree Celsius. His original scale set 0 degrees Celsius as the boiling point of water and 100 degrees Celsius as the freezing point. Why? Remember the thermoscope? The liquid level dropped at higher temperatures and rose at lower temperatures due to the expansion and contraction of air. This reverse scale was later inverted after his death by Carl Linnaeus, a botanist, making 0 degrees Celsius the freezing point and 100 degrees Celsius the boiling point. Kelvin scale, developed by William Thomson, 1st Baron Kelvin, 1824 to 1907. Year, 1848. Key concept, absolute zero as the starting point for a thermodynamic temperature scale. Lord Kelvin, a British physicist and engineer, developed the Kelvin scale to address the needs of thermodynamics, a growing field of physics at the time. He introduced the concept of absolute zero, 0K, the theoretical temperature at which all molecular motion ceases. The Kelvin scale uses the same increments as the Celsius scale, with a key difference. 0K is absolute zero, and there are no negative temperatures on this scale. This scale is widely used in scientific research because of its direct relationship with the laws of thermodynamics and energy. The Kelvin scale is the SI unit of temperature. Kelvin does not use degrees. It's simply written as K. Conversion. The Kelvin scale is essentially a shifted version of the Celsius scale that begins at absolute zero, but both scales use the same size unit increment. This makes it straightforward to move between the two. The Celsius and Kelvin scales are related by a simple linear equation. The relationship between them is Tk equals Tc plus 273.15. To convert from Celsius to Kelvin, add 273.15 to the Celsius temperature. To convert from Kelvin to Celsius, subtract 273.15 from the Kelvin temperature. Examples. 1. 25 degrees Celsius in Kelvin. Tk equals 25 plus 273.15 is equal to 298.15. 2. 310 K in Celsius. Tc equals 310 minus 273.15 is equal to 36.85 degrees Celsius. The Celsius and Fahrenheit temperature scales use different 0 points and increments. The freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit. The boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. The relationship between the Celsius and Fahrenheit temperature scales is linear and can be expressed with the following formulas. 1. Converting Celsius to Fahrenheit. Degrees Fahrenheit equals degrees Celsius times 9 divided by 5 plus 32. 2. Converting Fahrenheit to Celsius. Degrees Celsius equals degrees Fahrenheit minus 32 times 5 divided by 9. Examples. 1. Convert 25 degrees Celsius to Fahrenheit. Degrees Fahrenheit equals 25 times 9 divided by 5 plus 32 is equal to 77 degrees Fahrenheit. 2. Convert 77 degrees Fahrenheit to Celsius. Degrees Celsius equals 77 minus 32 times 5 divided by 9 equals 25 degrees Celsius. 3. Convert minus 10 degrees Celsius to Fahrenheit. Degrees Fahrenheit equals minus 10 times 9 divided by 5 plus 32 is equal to 14 degrees Fahrenheit. 4. Convert 50 degrees Fahrenheit to Celsius. Degrees Celsius equals 50 minus 32 times 5 divided by 9 is equal to 10 degrees Celsius. Keep in mind that the relationships between temperature scales are exact, meaning the numbers in these formulas do not influence the significant figures of your results during conversions. Why doesn't the temperature go below minus 273 degrees? Jacques Charles, in 1787, discovered that the volume of a gas at constant pressure increases linearly with temperature. His experimental data suggested Vt equals V0 times 1 plus alpha T, where V0 and Vt are the volumes at 0 and T degrees Celsius, respectively, and alpha is the thermal expansion coefficient. Joseph Louis Gay-Lussac, in 1802, experimentally verified and generalized Charles's work, determining the same linear relationship. Charles and Gay-Lussac's work relied on the Celsius temperature scale and did not explain why gas volumes appeared to approach zero at minus 273.15 degrees Celsius. Based on the data from Charles and Gay-Lussac, Kelvin recognized that the volume of an ideal gas would theoretically shrink to zero at minus 273.15 degrees Celsius. Since volume cannot have a negative value, this represents the lowest possible temperature. Are alcohol and mercury the only liquids used in liquid-in-glass thermometers? No, alcohol and mercury are not the only liquids used in liquid-in-glass thermometers. While alcohol and mercury are historically the most well-known liquids for thermometers, many other liquids, like toluene, silicone oil, and Gallinstan, are used in modern thermometers to cater to specific temperature ranges, environmental conditions, and safety requirements. The choice depends on the thermometer's application and the desired temperature range. If a thermometer is based on the height change due to the thermal expansion of the liquid inside a column, how can one ensure that the volume of the column itself remains fixed despite temperature changes? Ensuring that the volume of the glass column remains stable despite temperature changes is critical for the accuracy of liquid-in-glass thermometers. This was addressed by careful material selection and design. Here's how. 1. Use of low-expansion glass. Early thermometers were made from materials like soda-lime glass or borosilicate glass, which have low thermal expansion coefficients. Borosilicate glass, in particular, resists expansion and contraction with temperature changes, minimizing errors. The minimal expansion of the glass ensures that the liquid's height change is primarily due to its own thermal expansion, not the container's deformation. 2. Calibration at fixed reference points. Thermometers were calibrated at 2 fixed and well-defined temperatures, such as the freezing point and the boiling point of water at standard atmospheric pressure. Any minor expansion of the glass during calibration was effectively baked into the scale, ensuring accuracy within the operating range. 3. Uniform thickness of the glass tube. The glass tube was manufactured to have consistent thickness along its length. Variations in thickness could lead to uneven expansion, distorting the liquid column's movement. Uniformity ensured that any small expansion of the glass was proportional along the entire column, minimizing impact. 4. Small bore diameter. Thermometers used a very fine bore, the inner tube containing the liquid, where even slight changes in liquid volume caused noticeable height changes. This design amplified the liquid's response to temperature while making the glass's expansion negligible in comparison. 5. Use of stable materials for the liquid. The choice of mercury or alcohol was strategic, as these liquids expand much more significantly than the glass does. This difference in expansion rates further ensured that the liquid's height changes dominated the temperature readings. 6. Limited operating range. Liquid and glass thermometers were typically designed for specific temperature ranges, where the expansion properties of the glass remained linear and predictable. Beyond this range, both the liquid and the glass could behave non-linearly, compromising accuracy. By combining low-expansion materials, precision manufacturing, and careful calibration, scientists like Anders Celsius could minimize the effects of glass expansion and achieve reliable temperature measurements. Suppose the ambient temperature was 1 degrees Celsius yesterday and 5 degrees Celsius today. Can we say today is 5 times hotter than yesterday? No, we cannot say that today is 5 times hotter than yesterday based on the Celsius temperature scale. Here's why. The Celsius scale is a relative temperature scale. The 0 point on this scale is arbitrary and not an absolute measure of heat. To compare how hot or cold something is in a multiplicative sense, we must use the Kelvin scale, which starts at absolute 0, 0 Kelvin, where all molecular motion stops. Converting the Celsius temperatures to Kelvin. Yesterday, 1 degree Celsius equals 274.15 Kelvin. Today, 5 degrees Celsius equals 278.15 Kelvin. 278.15 divided by 274.15 is equal to 1.015. This means today is only 1.5% hotter than yesterday in terms of absolute temperature, not 5 times hotter.
Okay, let's turn up the heat. Play this game and show off your temperature conversion skills.